Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class we were discussing about method of successive averages. So, we will continue in that direction. So, if the perceived link travel times are assumed to be normally distributed, then these values, that is the probability of finding uh, path k given the OD pair RS and given these measured travel times CRSN at the nth iteration of this algorithm, we will have to follow the probit model. Okay, and in other applications, one can also follow that uh, these probabilities are given by logit model if we assume that the perceived link travel times uh, satisfy the required assumptions. So, note that this method of successive averages, although we have introduced it to solve the stochastic user equilibrium problem, but it is also applicable to solve the deterministic user equilibrium problem. Okay, because the stochastic user equilibrium problem is an extension of the deterministic user equilibrium problem that we had seen before. So, if this algorithm is applicable for the stochastic user equilibrium problem, definitely it will be able to solve the deterministic user equilibrium problem. Okay, so when the um, error terms associated with the travel times um, are 0, so then this stochastic user equilibrium case boils down to the deterministic user equilibrium case, and therefore the method of successive averages will directly apply. Just the only thing is that when we apply the method of successive averages for solving the deterministic user equilibrium problem, so in that case, when we will be applying this step of network loading procedure, so then we will be actually be doing all or nothing assignment in that step. Okay, because in this method of successive averages step, um, we had just mentioned that we use the required network loading procedure given that we have the set of measured travel times. Okay, so uh, depending on whether it is the case of stochastic user equilibrium or the deterministic user equilibrium, the appropriate network loading procedure has to be used. Okay, so in the case of deterministic user equilibrium, this network loading procedure is the same as all or nothing assignment, and in the case of stochastic user equilibrium, depending upon what assumption that we make on the perceived link travel times, we can either assume the network loading procedure to be given by the probit model or it can be given by the logit model. Okay. So, this method of successive averages will also converge to the optimal solution even if we use it to solve the deterministic user equilibrium problem rather than using the convex combination method that we had seen before. However, the convergence of this algorithm will be slower than that of the convex combination method. Okay, and that is the reason when we had discussed about the deterministic user equilibrium problem. So then we had specifically introduced convex combination method. Although at that time we could have introduced the method of successive averages also, which would have been applicable in this stochastic user equilibrium case also. But the reason for not doing that was this convex combination method is faster in convergence as compared to the method of successive averages when we are solving the deterministic user equilibrium problem. So, note that in this method of successive averages, the initialization step can be based on the free flow travel times. Okay. That is, when we mention that we have to take the inputs of this T0A, so that means that we assign 0 flow to every link, and depending on that and the link performance functions that we choose, we get the measured travel times for initialization. Okay, and that we can use for the initialization step. So, those travel times are the free flow travel times because we are assigning 0 flow to the flow in every link, and then we are determining the link travel time based on the link performance functions. Note that the termination criteria in method of successive averages is slightly different as compared to the previously discussed criteria because the convergence of MSA is not monotonic. So, if you recall, the convergence of the convex combination method was monotonic, that is, we were seeing a gradual or a continuous change in the uh, objective function value, that is the objective function value, for example, uh, was either only decreasing or increasing depending upon whether we are maximizing or minimizing, okay, as the number of iterations passed, but that may not be the case in the method of successive averages. So, in order to ensure that thing, so the termination criteria is defined to be slightly different in the method of successive averages. So, we try to look at how does the solution change over the last few given iterations. So, suppose m is the number of iterations which we want to take into account while determining the termination criteria. Okay. So, let x a bar n denote the flow averaged over the last m iterations for link A. Okay. So, suppose if a given link has flows equal to 10, 15 and 20 in the last 3 iterations. So, we will be taking the average of that and then that is the x a bar n value for that link, given that m is equal to 3. Okay. That is, we are concerned about the last 3 iterations while determining the termination criterion. So, this is the expression for determining this flow that is averaged over the last m iterations for a given link A. So, here you can see that there is 1 by m here because we are considering last m iterations here. This is the flow in that link in the last iteration that we have considered so far, that is nth iteration, then this is the flow in link A at n minus 1 iteration and so on, and we go until the iteration n minus m plus 1. Okay. And this expression can be written in a more compact form in this way. Okay. So, here L is starting from 0 to m minus 1. So, you can cross check. So, for example, when you put L equal to 0 here, this value is equal to x a n, which corresponds to this. Okay. Whereas, when you put L equal to m minus 1, this will be n minus m plus 1, which corresponds to this. Okay. So, this is the compact way of writing down the flow that is averaged over the last m iterations for link A. So, the number of iterations that we want to consider while determining this termination criteria, that is m. So, this needs to be fixed before. So, we need to determine before starting our algorithm that what is the value of m that we want to choose. For example, this m equal to 3 can be one reasonable value that one can consider. Okay. Therefore, the following criteria based on the flow similarity in conjugation with x bar n can be used. So, here on the left hand side we have this in the numerator we have the square root of the sum of the square terms where we have these differences x a bar n plus 1 minus x a bar n. Okay. And then we are dividing it by this sum x a bar n, where the sum is going over all the links. Okay. And this ratio should be less than or equal to some predefined threshold kappa that we have. Okay. So, in a way what we are doing here is that for every link A, we are trying to see how much is this difference of the flow that is averaged over the last m iterations when we consider the last iteration to be n plus 1 versus when we consider the last iteration to be n. Okay. So, we determine that value, we square it and then we sum it over all the links A and then we take the square root of that. Okay. And then we divide it by the sum of these flow that is averaged for different links while considering the last m iterations when the last iteration is n. Okay. Okay, and one more important point here is that while considering this method of successive averages, uh, until now we have only considered that this alpha n equal to 1 by n is one possible um, sequence that is useful for determining the move size. Okay, but this is not the only one that satisfies the conditions from MSA. Okay. For example, any such sequence where alpha n is equal to k1 divided by k2 plus n, where k1 is positive and k2 is non-negative, can be used. Okay. So, if you recall, in the beginning we had discussed two conditions that the sequence alpha n should satisfy. Okay. So, you can go back and you can try to see that there were two conditions, that is, one kind of sum related to alpha n should be tending towards infinity and one kind of sum should be finite, that is, it should not be tending to infinity. Okay. So, those two conditions can be satisfied if you choose alpha n to be on this way. Okay. For example, if you choose k1 to be say 1 and k2 to be equal to 3, that is also fine. So, 1 divided by 3 plus n, this kind of sequence if you choose, that will also satisfy the two conditions for alpha n that we had seen in the beginning of the discussion of method of successive averages. Okay. So, this alpha n equal to 1 by n is not the only possible move size sequence that will ensure convergence of the method of successive averages. Okay. Okay. So, now let us consider an example here. So, suppose that we have this network where we have a single origin and a single destination, and there are two links which are connecting these OD pair. So, suppose the link performance functions or the travel time functions are given by these expressions here. So, here x1 is the flow on link 1 and x2 is the flow on link 2. So, let us assume that we are considering the logit route choice model here. Okay. So, that means that we will be considering this logit route choice model during the network loading process. Okay. It is also given that the total demand from origin to destination is 4000 units and the logit parameter theta is given to be 1 unit. Okay. Now, since this is a very simple example, we can find the solution through the equilibrium condition that we had seen before. Okay. So, if you recall, this is the equilibrium condition that we had discussed before. So, here x1 is the flow on link 1 divided by the total demand. Okay. So, that is the probability of choosing this first link. So, since we are assuming the logit route choice model for the network loading procedure, so this is the expression that we get. Since there are only two alternatives here, that is, there are only two links here. So, this is the expression that we get. Okay. So, here T1 and T2 are the major travel times. Okay. Now, one can easily solve this, okay, because T1 will be given by, since T1 is the major travel time on link 1. So, if you remember in the stochastic user equilibrium case, we assume that the expected travel time is the major travel time, okay, and that is given by the link performance value. Okay. So, for T1 here you can replace the expression of the link performance function that we just saw in the previous slide. Okay. So, that is a function of x1. Again, for T2 also you can replace it with the travel time function that was shown in the last slide. So, then you will be getting a whole function which is having x1 and x2 on the RHS. Now, we also know that the x1 plus x2 will be equal to the total demand, which is equal to 4000, that is given. Okay. And q here you can put it to 4000 and theta is given to be 1. Okay. So, you have this equation and you have this equation. You can replace x2 with 4000 minus x1 in this equation, and then one can solve it. Now, this equation has to be solved using a numerical method. Okay. So, we have seen this kind of examples before. So, once we use any appropriate numerical method, then one will be getting that x1 is equal to 1845 units. Okay. So, this is the amount of flow that will take place in the stochastic user equilibrium case for this given example. And automatically once x1 is there, you can calculate x2 to be equal to 4000 minus this quantity. Okay. Now, this solution that we found out was using the equilibrium conditions directly, but if a very complicated network is given, then solving the equilibrium conditions may not be very easy. Okay. And that is why we have developed this method of successive averages that will be able to efficiently solve the problem for very complex cases. Okay. So, that is why now we will also check what solution we get, suppose if we solve the same example using the method of successive averages. Now, note that we do not need to formulate the equivalent stochastic user equilibrium optimization formulation, as that is not explicitly used in the solution procedure of MSA. Okay. So, we can just go ahead with using this MSA. So, in that we need to fix the move size sequence that we will be using. Okay. So, let us assume that alpha n is equal to 3 by n. Okay. So, this kind of move size sequence is fine. I mean, there is no issue with that, because we saw that we can choose any sequence of this type, alpha n equal to k1 by k2 plus n, okay, where k2 has to be non-negative and k1 has to be positive. So, here in this case we have chosen k1 to be equal to 3 and k2 to be equal to 0, and that is how we get this alpha n. Okay. So, with this kind of alpha n also, the two conditions that we had seen on the move size in the beginning, those will be satisfied related to the convergence, and therefore, this move size sequence is fine. Okay. So, here this figure is showing that if one uses the method of successive averages, so what is the flow on link 1 that we get as the iterations of this algorithm proceed. Okay. So, you can see here that there is this zigzag pattern here. So, sometimes the flow on link 1 is increasing, and in the next iteration it is decreasing, then it is again increasing, and so on. Okay. So, this is a kind of a different pattern here. But the pattern is still relatively smooth and well behaved, in the sense that you can see that although sometimes the flow on link 1 is increasing and then decreasing and increasing again, we can see that overall in the average sense the flow on this link 1 is kind of converging towards a particular value, which is here. Okay. So, in general, this algorithm, that is the method of successive averages, can be expected to converge faster with lower values of q and theta. Why is that? Because first thing is that lower values of q indicate low congestion, and implying that small changes in the mean travel time between the successive iterations. Okay. And low values of theta indicate large perception variance. Okay. So, when large perception variance is there, then under such circumstances the mean travel time is less important and the perception plays more important role. Okay. And therefore, the convergence become faster, because now you do not have to rely more on the mean travel time values, which may change with the iterations. Okay. So, since the reliance on mean travel time has reduced, so therefore, the convergence becomes faster in that case. Okay. So, in this case you can see that this figure is now showing how the flow on link 1 will change with the iterations of this method of successive averages when we choose this theta to be equal to 1. So, this is the same as before, but now this total demand is equal to 2000 as compared to 4000 before. So, now the Q has decreased. Okay, so the total demand is decreased. You can think of it in this way, that the total congestion across the network has decreased. So, now there is less reliance on the mean travel time values, and therefore, you can see that the convergence is faster here, that is here. So, this is saying the same thing, that this figure is showing corresponding to theta equal to 1, but Q is equal to 2000 now, and the convergence is now reaching in just 4 iterations. Previously, in the figure that we had seen in the last slide, the convergence was taking about 20 iterations, but this time it is only taking 4 iterations because Q is lower as compared to before. Okay, so the congestion is less, and the reliance on the mean travel time values is also less. Okay, now what we are doing here is that we have increased the theta value. Okay. So, now the perception variance is now lower. Okay. So, now since the perception variance is lower, there is more reliance on the mean travel time values, and therefore, the convergence has become slower. Okay. So, now you can see that as compared to the previous figure where theta was equal to 1 and Q was equal to 2000, now the convergence is happening in 7 iterations as compared to the 4 iterations that was happening before. Okay. So, these 3 figures that we have seen in these last 3 slides here, so they are showing the variation of the convergence with different theta and Q values. Okay. So, with this we end here the discussion on the method of successive averages, and also the discussion on the stochastic user equilibrium case. So, now we will be starting a very different topic here. So, here in this topic we will be considering the interactions between different links here. So, previously we had assumed that the travel time of a given link is the function of the flow on that link only. Okay. So, now we will be considering the cases where this assumption may not hold true. Okay. But what we will be doing here is that while we are going through this new case, we will be assuming that it is still the deterministic user equilibrium. Okay. So, this case will also be an extension of the deterministic user equilibrium case, the basic version that we had seen in the first time. So, this is now another extension of that case. So, the stochastic user equilibrium case was also an extension of the deterministic user equilibrium case, but in a different way. That is, there we were assuming that there can be some error in the travel times, and that is why the perceived travel times were assumed to be random. Now, we are considering another extension of the deterministic user equilibrium problem that we had seen before, where now although we are assuming that the user equilibrium is deterministic, that is there is no error in the travel times, but the link travel times can have some interactions. Okay. So, let us start this topic here. So, we assumed in the deterministic version of the user equilibrium that the travel time on a given link depends only on the flow through that link and not the flow on any other link. Okay. That is, mathematically, the partial derivative of the travel time on link A with respect to the flow on link B, we assumed it to be equal to 0, where A and B are not the same links. Okay. However, the flow interactions cannot be ignored when there is heavy traffic in two-way streets, or when we have unsignalized intersections and so on. Okay. So, for these cases, we just cannot assume that the travel time on a given link will only be dependent upon the flow on that link. Okay. So, when we will move along, we will be considering these cases, and then it will be easier to understand. So, therefore, we will be focusing on user equilibrium when the flow interactions are allowed. Okay. So, we will first focus on link interaction between two links, but these two links are in opposite direction, okay, and these can represent two-way streets in the real world. Okay. So, this analysis that we will be presenting can hold for any pairwise symmetric link interaction pattern, and it is not just restricted to these two-way streets. Okay. So, in this two-way street case, as the traffic builds up in one direction, the delay to flow in the opposite direction increases due to, for example, the reduction in passing opportunities. Okay. So, we are now considering this case where we have two-way streets here, and there is no barrier between them. Okay. So, in that case, we can safely assume that the travel time on one given direction will not just be the function of the flow in that direction. If, for example, the flow on the other direction starts to increase, then there will be impact on the travel time in this given direction also, because for this direction it may happen that the passing opportunities or the space that is available is sometimes getting reduced and so on. Okay. So, therefore, the travel time on any given direction will be dependent upon the flows in both the directions. Okay. So, this effect can become quite pronounced in moderate to heavy flow. Okay. So, this kind of interaction is only meaningful when there is significant flow in both the directions in the two-way streets. Okay. So, when the interaction is not significant, for example, when the flows in both the two directions are so low, then there might not be any interactions, and then considering that the travel time in one direction will be a function of both the flows will not be correct precisely. So, in that case it is not very useful, but only when the traffic flow is moderate or heavy, then this kind of assumption is useful. Okay. So, with this we will be continuing about the link interactions and so on in the next class, and let us end it here then. Thank you.